You travel in a spaceship to Mars. We will approximate your ship as a sphere of radius 10 meters and take its emissivity as 1.0. Part A. Assuming the surface of your ship is at the same 290 degrees Kelvin as the interior, what is the rate at which the ship loses heat via radiation in watts? The Stefan-Boltzmann equation is the one that tells us the heat rate due to radiation. This equation has first the emissivity, which is a unitless constant from 0 to 1. Next, the Stefan-Boltzmann constant itself, which is 5.67 times 10 to the minus 8. The area from which the heat is radiating, and the temperature to the fourth power. In the case of our spaceship losing heat, we've been asked to take the emissivity as 1.0. This means that the surface of the ship is both perfectly absorbing and at the same time perfectly emitting of blackbody radiation. The Stefan-Boltzmann constant is always 5.67 times 10 to the minus 8. And for the area, we need to be cognizant of the fact that our ship is shaped like a sphere. Therefore, the area from which we are radiating this heat into the vacuum is the shell of the sphere of our ship. The area of a spherical shell is 4 pi times the radius of that shell squared. In our case, the radius is 10 meters, and so we'll put in 10 squared as the area. Finally, looking at the temperature formula, we recognize that this is not a delta T relationship. The T stands alone. And for this reason, we must use the T in Kelvin, and we've fortunately been given this already as 290 Kelvin. Plugging in all of these numbers, we find that the rate at which heat is leaving your ship via radiation is 504,000 watts. In Part B, we're going to begin to account for the fact that you're not out in deep space, you're near our sun, and that will result in heat also coming into your spacecraft. Beginning, we see that Part B says the sun has a radius of 695 billion meters and a surface temperature of roughly 5,800 Kelvin. How many watts per square meter are emitted from the sun's surface by radiation? We'll take the sun also to be a perfect black body, so that when we evaluate its emissivity, we'll be using 1.0, and thus we get the result for the total rate at which the sun is radiating heat of 1.0 times the Stefan-Boltzmann constant times the area of the surface of the sun. Since the sun is a sphere, the area of a spherical surface is 4 pi times its radius squared. And finally, we have the 5,800 Kelvin to the fourth power. Plugging in all these numbers, we find the total rate at which energy leaves the sun is equal to 3.89 times 10 to the 26 watts. As we expected, the sun is an impressively strong source of power. Let's move on to Part C. Fortunately for you, you are much further than only 695,000 kilometers from the center of the sun. You are 1.5 billion meters from its center. How many watts per square meter is the sunlight intensity at your ship? Well, we know from the previous problem that the sun produces about 4 times 10 to the 26 watts. To make this into an intensity in watts per square meter, we have to imagine how far this sunlight has been stretched out. If we place the sun as this black dot in the center, we can then imagine what's happening at your spaceship, which is 150 billion meters from there. The answer is that the light itself has spread out over a very large surface, which is shaped like a sphere whose center is at the sun. Therefore, since we recognize that at every point on the surface of this sphere the light has exactly the same intensity, we know to take the total of about 4 times 10 to the 26 watts and divide it by the area of this sphere to get the intensity at your location. Thus, at your location, the intensity is going to be equal to the total power of the sun, which is 3.89 times 10 to the 26 watts, divided by the area of the large sphere over which this power is spread out, and that is a spherical shell whose radius is 150 times 10 to the 9 meters. This means that the intensity of the sun at your location turns out to be 1376 watts per meter squared. Part D asks, how many watts do we receive from the sun? Well, if we imagine, going back to the figure from Part C, this spherical wave of energy leaving from the sun, when that spherical wave of energy impinges on our spaceship cuts from that a circular hole of radius 10 meters. Therefore, the missing piece of energy is a circle whose area is pi r squared with 10 meters. The power that we receive from the sun is therefore equal to the intensity of 1376 watts per square meter times the area of pi times the radius of our spherical spaceship squared. This is 432,000 watts. Finally, Part E asks us whether we worry most about frying or freezing. Well, since the outgoing power in the form of heat radiating from our spaceship is 504,000 watts, and the incoming power from the sun itself is only 432,000 watts, the outgoing heat exceeds the incoming heat, and so in fact our major concern is freezing. One thing you might ask yourself, why is it that these two numbers, 504,000, 432,000, they came within about 20% of one another? Boy, is that some sort of an accident? The answer is no. The 150 billion meters from the center of the sun is roughly the distance from the sun to the Earth. So in fact, given the rate at which energy enters the Earth due to the sun, and the rate at which it goes out into space due to radiant heating, we get room temperature on Earth, or about 20 degrees Celsius. That's why in this problem, these two factors are nearly balanced, and we're not so close either to freezing or frying.